So, we were talking about the physics of welding arc, and there are few, irrespective of the welding process, there few things are very common. So, I have talked about the polarity also, like the AC or DC, straight polarity or DC, reverse polarity, and its effect on the heat generation as well as the arc stability. Today I will talk about the few things like one is the arc stability, sorry, arc initiation. Arc initiation. How do we strike the arc? So basically, it is just like when you have a power source, okay, and it is connected to the electrode, and this is the workpiece. So initially, certainly there is no arc. So what we do, we use so to strike this welding arc, what we do, we the two methods. There are basically two methods. One is called touch start method for arc initiation, and the second is the field start. Okay, so the touch start method, what we do, the electrode is brought in contact with the workpiece where arc is to be striked. Say this is the location. So what we do, electrode is brought in contact with the workpiece so that your circuit is completed, because it is connected like this. So circuit is completed. So when there is a circuit completion, short circuiting is happening. So there is a flow of very high current, high I value. So at the interface, lot of heating due to the I square RT, and so that will be taking place. So there is a rise in temperature at the tip of the electrode. So whenever there is a rise in temperature at the tip of electrode, by thermoionic emission, the electrons are emitted. So what we do, once the electrode has been brought in contact with the workpiece, we try to move it apart. Okay, so initially we touch for a while so that the circuit is completed, and then we move the electrode apart so that arc gap is established. And since you have already emitted thermoionically, you have emitted the electrons at the tip of the electrode, so the gap becomes conducting and the current flow starts. So this is the simple approach of the touch start method, where the electrode and the workpiece are connected to the power source terminals. Then electrode is brought in contact with the workpiece so that the circuit is completed, and in this process of the circuit completion, lot of thermoionic heating takes place. So because of that, thermoionic emission of the electrons occurs, and when the electrode is moved apart, the gap is created which is full of the free electrons. So if the gap becomes conducting, and that's how arc is struck. This is one method, and this is mostly used for like say in shielded metal arc welding process. This is also known as a stick electrode welding process. The touch start is very commonly used, but not in all the processes. Like also in MIG welding we can use the touch start, or so this is submerged arc welding also, it can be the touch start. So but there are many processes where we want that electrode doesn't touch the workpiece, because say electrode is non-consumable in case of like tungsten inert gas welding or in plasma arc welding. So electrode in both the cases is made of tungsten and it doesn't melt. It is expected that it will not be heated much. So what we want, that without touching of the electrode to the workpiece, if we can strike the arc between the two. So what we do, we try to establish the high potential difference between the two. So the electromagnetic field is established. Okay, so because of this electromagnetic field, what happens, that electrons are pulled out from the surface of the electrode. So this method, where high strength electromagnetic field is established by applying high potential difference of about 10 to the power 7 volt per centimeter. So that's the kind of the high potential difference which is established across just for a short while. It's for very short while. And one typical device known as high frequency HF, high frequency converter, is used for this purpose. So HF unit supplies such a high voltage for a very short while, so that high potential difference is established across the electrode and workpiece, and the electrons are emitted. This is the second method. So these are the two methods which are commonly used for arc initiation. One is your touch start and another is field start. Okay. There is one more simpler method which is a variant of the touch start method only. Like in this case, what we do, we use one carbon block like this. Okay, and these are the components to be joined and weld is to be made here. So what we do, we put the carbon block adjacent to the workpiece to be welded. Okay, so this is basically carbon block. So what we do, electrode is brought in contact with the carbon block and then it is moved to the location where, once the arc is struck, it is the electrode is moved to the location where welding heat is needed. So in carbon block method, basically the electrode is brought in contact with the carbon block and then it is quickly moved towards the location where arc is needed. The advantage is that of this method, you see, you directly supply the heat to the workpiece and there is no striking of the arc here and there with the base metal, but arc is struck or initiated with the carbon block itself. So this is the third method, you can say. It is based on, it is just a variant of the touch start method, because in any case we have to touch the carbon block using the electrode. Now, what these electrodes are basically, there are two types of the electrodes which are used in all welding processes. One is your in arc welding, or in all arc welding processes, not all welding, because in many welding processes you don't use the arc. There is no welding arc for developing the heat or developing the joint. So mostly in case of the arc welding, two types of the electrodes are used. One is called non-consumable electrode. Okay, mostly the tungsten or coated tungsten electrodes, tungsten pure or thorium or zirconium coated tungsten electrodes are used. These are mostly used in case of the plasma arc welding and the tungsten inert gas welding. These are the two processes. While in case of the consumable, so in non-consumable arc welding process, your electrode remains intact. It is expected that it just helps to strike the arc. It is not consumed. It doesn't provide the filler metal. Filler metal you have to feed from additional source from outside. Okay, so there is no consumption of the electrode in these processes, plasma arc and the TIG welding. Okay, but in consumable arc welding processes, where the consumable electrode is used, another type of electrode is where electrode is consumed. So here in non-consumable electrode primarily helps to strike the arc only. Okay, no melting. But in case of the consumable electrode performs both roles. It strikes the welding arc, number one, and second, it provides the molten metal. For filling the gap or for developing the weld joint. So both the roles are performed by the electrode in case of consumable electrode welding processes. So the whole range of the consumable electrode welding processes include like shielded metal arc welding process, SMAW, your submerged arc welding process, MIG welding, your flux core arc welding, FCAW, your electro slag, okay, welding, and electro glass welding. In all these cases, electro gas welding. Okay, electrode. So in all these process, the arc is struck between the electrode and the workpiece. Okay, like this. So arc like wire will be melting also during the providing the molten metal to develop the weld joint. Okay, so here, since the electrode is consumed, you see the interesting part is electrode is consumed, so it has to be replaced. So in some cases like submerged arc welding, MIG welding, what we use the spool of the electrode, so it is fed continuously. Okay, once the spool is over, then it is replaced with a new set. But in case same is true for your electro slag welding, electro gas welding, and even FCAW as well, flux core arc welding. In all these processes, you see very lengthy electrode which is wrapped in form of this spool that will be used to feed the electrode to the welding process. Okay, in all these welding processes, so this will be helping to develop the weld continuously. You see, you can weld in meters without need of replacing the electrode. But in case of the SMAW process, your electrode is of limited length, like say 300 to 450 mm in length. So once it is consumed, you have to throw it away and you have to replace it with a new one. So there will be a lot of interruptions. So the point here is, if you are doing a welding for very longer length, then one electrode may be able to do up to this end, then you have to change it, then use another electrode again up to this, then again electrode. So the process is interrupted in case of the SMAW. So this is the disadvantage. It will be, the process has to be stopped, then electrode has to be changed, and then a new electrode is to be replaced. So this will be slowing down the process. So that is good for general welding purpose, for repair purposes, or for little or minor fabrication works. But if for mass production purposes, where extensively longer lengths like shipbuilding or pressure vessels, where extensive welding is needed, then probably it is preferred to use this consumable electrode arc welding process like submerged arc welding, MIG welding, or FCAW. So where you can feed the electrode continuously without stopping so frequently. So this in turn will be helping it to achieve the higher deposition rate. Deposition rates are very interesting, no? Like say in what quantity you are depositing the weld metal in 1 hour. So it may range say from 1.5 to 2 kg per hour for simpler welding, 2 kg per hour. Okay, for like say SMAW or GTAW kind of processes. Okay, where we have to feed the electrode from outside. But like submerged arc welding, it may be like say 5 to 7 kg per hour also for submerged arc welding processes. So the point here is how much time you are taking to develop the weld joint. That will depend upon at what rate you are depositing. So higher the deposition rate, lesser will be the time it will be taking. Okay, just for an example, if this is the very large size the joint is to be made, then it will take very long to develop the desired to weld. Okay, because of the low deposition rates. So high deposition rate certainly will be helping you to complete the welding in shorter time. Okay, that's all. That was about the consumable electrodes and the kind of consumption rate or deposition rate. As far as these welding processes are concerned, the welding processes, arc welding processes especially, use the two types of the power sources. Okay, the one is, you can say, AC, and another is DC. DC is preferred for number of situations where you have the choice for heat generation as per your need. Okay, and your arc stability is also good when AC is used, when DC is used. So what is the what we use for generating the DC? So basically these are the generators, rectifiers, are commonly used as a power sources for developing the DC, and the transformer is so typical welding transformers are used for AC welding. Okay, there is a very interesting phenomena. Your domestic supply, what you get normally, it is 220 volt, and the kind of current that we use 5 ampere, 10 ampere as per the appliance being used. But in case of the welding, it is just opposite. Welding, so this is the domestic case. Okay, in welding we use just the in welding power sources, they do just the reverse thing. We use the low voltage and high current transformer power sources. So the power supply, power delivered by the welding transformers, they deliver us low voltage, which may be in the range of say 10 volt to say 50 volt is very common, and the current may range say from your nominal minimum 100 to like say even 2000 ampere of the current. So this is the difference in your domestic power supply systems and the welding power supply systems. In domestic power supply, you are using high voltage and low current, and otherwise we get in welding power sources, we use the low voltage and high current. Okay. So how do we choose the electrodes? So this is an important aspect. Like say, you see, the electrode choice. Let me tell you, probably I have talked about that earlier as well. Like say, these are the two components to be joined. So one simplest way is you apply the heat source and melt them together. In this case, we don't supply anything from outside, and this is the case where we don't feed anything, so it is autogeneous weld. Okay, but in these situations when we find that no, direct welding is not workable, or it is say this is good for thin sections. Okay, this is good enough for thin sections, but when you find that no, it is a thicker one, like say the thickness is more, so you have to feed, or so in that case you have to feed the molten metal from outside, because you have to prepare the groove like this, and then these grooves need to be filled in so that true thickness penetration can be realized. So what we use actually for this purpose, so in case of normally what we use, we try to go for the matching filler, which means the filler metal is matching with the base metal or the parent metal to be joined. This is the first thing. Hello, there is a disturbance. Can you mute yourself? Hello. Yeah, so this is the first parameter. The electrode selection primarily depends on the certain factors. So one is the choose the matching filler so that your weld metal properties are almost similar to that of the base metal. That's one. The second is the mechanical property requirement. Sometimes, you know, weld joints are known to offer very heterogeneous properties. I'll tell you how. So this is the fusion zone where you have got cast structure. This is the heat effector zone. So there is a lot of heterogeneity in microstructure and mechanical properties across the weld. Okay, if you want that the weld is made of a specific set of properties, like weld needs to be say very good corrosion resistance, one, you want very high toughness. So what we can do is we can choose the filler which can really offer those set of the properties that are desired. Okay, so in this case we may use completely different. I'll give completely different filler metal. I'll give you example, like say the cast iron is to be welded, CI. So CI is never welded using the CI filler, but what we use the nickel filler, or we use the austenitic stainless steel filler, because they are soft and they can help in developing the tough and the crack free the weld joint. Okay, otherwise if you weld it using the cast iron filler, then simply immediately after the welding you will get the lot of cracks in the weld joint itself. So what kind of properties you are looking for to achieve the desired properties in the weld joint? Accordingly we choose the filler. So one simplest case is use the matching filler, and if you want different set of the properties to deal with the specific requirements, then go for the properties in the filler that are expected or that are needed. Okay. The another important aspect is, like, we also look for, when electrode is being selected, we look for the thickness of the section size of the base metal to be joined. Like say if it is say just 5 mm or 50 mm or 20 mm based on that. So why we are talking about this, like when the thickness is very less, you need very less heat for through thickness penetration. You don't need to supply much of the heat, so it is possible like 150 ampere current may be good enough, okay, for 5 mm. But if it is say 20 mm, you may have to go for say 300 to 400 ampere current for realizing the through thickness penetration, okay. If it is 50 mm, then you may have to work for like say 1500 to 2000 ampere, so if you take, so when the current is low, you can work with these small diameter electrodes D, okay. When the current is more, you need little larger diameter. When current is further more, you need further larger diameter. So the diameter of the electrode is identified by the core diameter. Like say in typical electrode coatings, this is coating and this is the core wire. So core wire diameter indicates the electrode diameter, and common diameters are like 1.5456 like this, even 2.5, 1.6. These are some of the other electrode diameters. As a thumb rule, D into 40 to 35. This is the times by which the current can be allowed to flow. Otherwise, what will happen, because of high current flow, if the high current is flowing through the small diameter electrode, I square RT heating will cause the much earlier melting than when. So it will become soft and you may not be able to weld the things properly. So the simple thing, increase in thickness increases the heat requirement, increases the current requirement, increases the electrode diameter needed. This is the simple logic. So increasing that thickness requires the more heat generation for welding, which can be realized through the supply of the high current. And to sustain the high welding current, it is important that large diameter electrodes are used. And a simple relation between the diameter and the current is like this, where that the maximum current that can be flown or supplied for the electrode is about 35 to 40 times of the electrode diameter, okay. So this is just as a thumb rule. Welding currents are like that, depends a lot on the welding process, welding voltage or arc voltage that we will be using, that will depend on the welding process. Current is primarily one parameter which is used for regulating the heat. Arc power, I have told you, depends on the VI. So VI is usually very low. It is fixed for a given process. Say for TIG welding, it is just say 10 to 15 volt. For MIG welding, it may be a little more, say 20 volts, okay. So, but voltage we don't use to adjust the heat input, although it will affect the arc power, but that is not used. What we use, we change the current basically, whether you use 100 ampere, 150 ampere, 200 ampere, so that there is, because voltage will depend upon the kind of electrode and the process which is being used, and that is there is very narrow window for adjustment of the voltage. So that is not the method for changing the heat input or adjusting the heat generation, okay. So this was about your what I was talking, like thickness, okay, thickness of the section thickness. So what I've talked, electrode choice depends on the base metal, the mechanical property requirement, and thickness to be joined, okay. Then another one is the electrode selection also depends upon the which type of the power source we are using, AC or DC. Like there are certain types of the electrodes which are compatible with the AC only. So this is made using the suitable low ionization potential elements. So the electrodes to be used, they are added with the high amount of the low ionization potential elements like sodium, potassium, calcium, so that they strike the they emit the electrons very easily. So even when the current is zero, there is some conductivity in the arc gap, and the arc is still able to stabilize or strike. It doesn't get extinguished so easily. So use of the low ionization potential elements for AC. So that is very important. Like if there are certain electrodes which can be used for the AC, and obviously those electrodes will be having the high proportion of the low ionization potential elements so that they can emit the electrons very easily. For DC, you see, even you can use the bare electrode also, but it will be good if there is some percentage or some amount of the low ionization potential element. It will be good for the R pistol as well. Okay. So we have to consider if the given electrode, this is one aspect. The given electrode is having what kind of the composition of the electrode is, what kind of coatings are there. So based on that, we take a call of if we can use AC or DC. Normally, manufacturers recommend like which type of the electrode it is and with what it can be used. Okay. Then one more interesting part as far as the electrode choice is concerned, that's the welding position. Welding position. Okay, so welding position, I have already talked, like there is a flat or the horizontal flat welding, or this is also called downhand welding. Then there is a horizontal, then there is a vertical and overhead. These are the four most common welding positions. So in a flat welding position, it's the plates are in horizontal position and the weld is simply made. Okay, like this. So there is no issue as such with the generation of the high heat input in flat welding, because you can simply and easily place the molten metal wherever it is desired, and there is okay, just a minute. Now can you see? Can you hear? Hello?
Yes, sir.
Okay.
Yes, sir.
So in flat welding, you see, there is no issue as such regarding the control of the molten metal. Since in the in flat welding, you can easily place wherever the molten metal is desired. So even if you generate the high heat, it's fine. High heat generation is fine because the placement is easier. Okay, so you can work even with the large dia electrodes for faster welding. But in case of, like, say, horizontal welding, which is done in vertical, the plates are in vertical position, but the weld metal is placed in horizontal direction only, like this. So the plates are in vertical position like this, but the weld is made horizontally. And in vertical welding, you see, the plates are in vertical orientation of the plates is vertical, and the weld is made also in vertical position, like moving up from down to top to bottom or bottom to the top, like this. In both these cases, there is a tendency of the molten metal to fall down. So you see, because molten metal is being placed on the vertical surface, so there will be tendency to fall down. So you need a good control over the molten metal. And how it is possible? You see, you have to supply less heat. Okay, so there is a less temperature, high surface tension, okay, high viscosity. And when you have high viscosity, you see, the metal will not tend to fall so easily. Okay, so what we prefer for horizontal and vertical and overhead positions, we prefer to use the smaller diameter electrode. Okay, so that you use the lower current, lower VI, lower heat generation, lower temperatures, and better control over the molten metal because of the high viscosity and the high surface tension. Okay, this is how the welding position is affecting to the. That's fine, I think. So these are some of the important factors affecting the selection of the electrode. As I said, if you are welding steel, so you have to choose the steel filler of the matching composition, or steel electrode of the matching composition. This is one of the, like, similarly for aluminum fillers are to be used like this. But sometimes if you talk of the specific process, if you take in your syllabus, we have got certain types of the processes. What are those? Like, we have got the shielded metal arc welding process. This is one. Okay, now another process, this is also known as manual metal arc welding. Why? Because it is performed manually only. Okay, then we have the tungsten inert gas, GTAW, or this is also known as TIG welding. tungsten, gas tungsten arc welding or tungsten inert gas welding. Then there is a GMAW. This is also known as MIG welding, metal inert gas welding or gas metal arc welding. Okay, and this is used in you see there is another variant in MIG welding. We have to use inert gas like argon or helium, but there is another variant where we can use CO2 as well. Okay, then we have the submerged arc welding. Okay, then we have the electro slag welding and electro gas welding. These are the two similar type of the processes with a little difference. Okay, then we have the electron beam welding EBW and the laser beam welding. These are also of the similar type because these are of the high energy density processes. And then there are like the ultrasonic welding among the solid state joining process, and then the resistance welding, especially the spot welding. So these are the processes, huge range of the processes we have. Let us see how it can be covered. This has to be done really quite fast. Anyway, so starting with the shielded metal arc welding. Shielded metal arc welding. This is also known as manual metal arc welding. Okay. So what is the unique about this process? Okay, and how it is different? This is very popular. About 80% of the weld metal is deposited by this process. So because this is very simple for all general purposes, general applications. It's very simple, low cost, and easy to use. So easy to use, low cost, and very simple. It doesn't require much of the systems. So it uses just like say the welding power source of about 10 to 15 kg, and you connect it to the domestic power supply and you get the system. And then there is a cable, there is electrode holder, and then connect the electrode and then do the welding. It's very simple. This is a standalone on its own. It doesn't require any special shielding arrangement. That's the good part. No shielding, special shielding arrangement is needed for this. That's why it's very cheap and low cost, very simple, easy to use process. And lot of weld metal is deposited commercially. Out of the total weld metal deposited, is about 80% is deposited using the shielded metal arc welding process. What is unique about this and what makes it so popular? It uses a very simple electrode, like say it is the base metal. The matching composition is similar to the base metal, and this is coated with the like this is coated with the suitable fluxes. Okay, so here you have flux. Now there are a number of ingredients which are added in the flux, like the charcoal, and there is a carbon powder, sawdust, calcium carbonate, sodium, potassium, etc. There are a number of elements which are added. Probably about that I will talk a little later. So what's some of the most common one, like the calcium carbonate, charcoal, and the sawdust. Like you cut the wood and whatever dust is produced. So that is, and then sodium and potassium used as a binding agents, and likewise there is silica, number of other constituents are also added. These are added for some special purposes to achieve the specific purposes. So the diameter of the core wire is say small d, and the capital D is the diameter of the electrode with the coatings, capital D. So the capital D by small d, this is used to define the coating factor, how thick coating you have over the electrode. So light coated, it is very thin, like say 1 to 1.2, and a medium coated is 1.2 to 1.4, and heavily coated, so the coating is very thick, so 4.2, 1.4 to like say even up to 2. So just like this, when the coating is the thickness of the coating is almost double of the core wire. just like that. So this is how the coating factor is used to define the thickness of the flux over the core wire. Okay, so and this is defined using the coating factor kind of thing, and these are common constraints which are added. What is the purpose of this these the fluxes which are used in welding? Okay, so like say this is the core wire. Okay, and here it is connected to the power source. Okay, so the base metal, so and this is the coating, right? So your arc will be striked. You see, coating burns at lower rates as compared to the core wire. So always you see this is the coating and this is the core wire, like this. It goes in like this. So here your arc comes out like this. Okay, so the coating is projecting beyond the core wire. So this helps to constrict or reduce the diameter of an arc. That is in very simpler way, that helps to constrict the arc. So you see what is happening here. If you see, you see this is the arc will be generating a lot of heat. So the coating, this coating will be thermally decomposed, and it will produce CO and CO2, because there is a lot of charcoal, sawdust, calcium carbonate, etc. CO2 are produced. So these CO and CO2 will form some kind of the blanket, cover or shroud around the welding arc and the molten metal. Okay, like this. So the first role which is produced, which is offered by the first role or the function of the coating is to provide the shielding gases in form of CO2 and CO to the weld pool and arc, because if these atmospheric gases, oxygen and nitrogen, they get into the weld metal, they will form their oxides and nitrites, etc. So they will be acting as inclusions, porosity, etc. So we want to eliminate, we want to expel all these gases, and this role is performed by this flux coating. So flux coatings basically thermally decompose and produce the shielding gases. That's one. Okay, the second is the flux coatings are also added with certain constituents which will form the constituents which will be forming the, so basically slag forming elements are added in the flux. So what these do, if there is oxides and other impurities which are present in the weld metal, molten weld metal, these constituents acts with these impurities to form slag. So slag being lighter, it floats over the surface of the weld metal like this. Okay, so if there are impurities, the impurities will be interacting with the flux coatings and they will be forming the slag. Slag is lighter in weights, in density, sorry, so it will be floating, so it will cover the molten metal, reduces the cooling rate, and avoids the direct interaction between the molten metal with the oxygen and nitrogen of the air. Okay, so there are a number of good things. So basically the second role is of this flux coating is to provide elements or constituents to form slag after interaction with the impurities and the oxides. Third role is that these coatings are added with the low ionization potential elements like sodium, potassium, which easily emit the electrons whenever it is connected to the power source. So Basically it is easy electron emission by the low ionization potential elements. These help in arc stability of welding arc. So the point is simple. The coatings help in arc stability, improving the arc stability by due to the presence of these low ionization potential elements present in the coatings. Okay. Then the important role which is performed by this by these coatings is that if you want to add certain alloying elements, like say this is the core wire, so what you can do, you can add, if you want tungsten, if you want to add chromium or nickel, then you can simply add these alloying elements with the flux itself, with the coating. So we can say that controlled alloying can be achieved using the coatings. Okay, controlled alloying is can be achieved using these the flux coatings. Okay, so we have to add those alloying elements with the flux coating, so that during the welding with the arc heat, these will also will get melt and mix up with the weld metal. Okay, as I said, sometimes we add certain specific elements like silicon to adjust the viscosity of the slag and molten metal. So the viscosity of the slag and the molten metal is adjusted by adding certain elements with the flux coating, so that they will help to reduce the falling tendency of the weld metal when the odd position welding is performed in either vertical or in overhead positions. Okay. Another important role, you can say, these coatings are basically acts as an insulator. So even if accidentally it touches to the other conducting metal, short circuiting is avoided. So the coatings act as an insulator, and so direct short circuiting and the closing of the circuit is avoided by the electrode due to the accidental touching with the other metals. Okay, there is one more. Coatings also help in increasing the deposition rate. What we do, like say, if you want to increase the how do we calculate the deposition rate? Let us understand this. This is the core wire, okay, and this is the weld metal being generated. So core wire will be melting. Say it has melted, say half 6 gram it has melted, 60 gram it has melted. Okay, so how much of its portion has been deposited? Okay, here say if it is 60 or it is 55 or 50, so that will dictate the deposition efficiency. This is about the core wire. Okay, so it is 50 by 60 means we will get our deposition efficiency accordingly, because some of the molten metal will be falling here and there, and you may not be able to deposit entire amount in the weld metal due to the spattering or some other losses. Okay, so including evaporation. So what we do, we add certain elements in powder form with the flux coatings, and in calculation we don't count these powder being added with the coatings. So say 10 gram is coming from the flux and 60 gram or 55 gram is coming from the core wire melting. So you are actually depositing 65 gram, and melting the core wire is 60 gram only. Okay, so here the deposition is efficiency is greater than the 100%. So what we are doing, we are adding the powder to be added in the weld metal, or Just to increase the deposition rate, the powders of the required metal is added in the coating so that it also melts. So it is just about the way by which we are calculating. I think that's all about these coatings and their roles. The common types of the coatings are, there are certain common ways, common types of the coatings. These are like say the rutile type coating. Okay, this is basically titanium based, and there is a basic coating, cellulosic coating, okay, cellulosic flux. Then there is acidic flux. So these are the four most common types of the coatings. Okay, so for basically the tough welds, crack free welds, the basic coatings are used. For all common purposes, your rutile and the cellulosic coatings are used. Okay, I want to talk about the electrode classification. So electrode classification according to the Indian standard is indicated by the certain set of the letters. You see, according to the Indian standard, the electrode classification, electrode designation, electrode designation of SMAW, sealed metal arc welding electrode, is done using certain set of letters and numbers which are written in particular sequence. So the set of letters and numbers written in particular sequence only. If there is any alteration of the sequence, then it will be incorrect designation. Okay, so what it shows, the first is the letter which shows the method of manufacturing of the electrode. So we can use either letter E or R, this one. Then we have the set of numbers 1 to 9. The character is the number which shows the type of coating being used. Second number indicates, like number can be anything from 1 to 9, that indicates the welding position in which welding is to be done. Again, the third character is a number, also it can be in range from 1 to 9. It shows the welding current. To be used. It can be AC, DC, and its magnitude. Then we have set of 3 numbers like 311, 411, 511. These indicates the set of mechanical properties of the weld metal. And in the ends we have again letters for special characters or special features of the electrode, like this. Okay, so for electrode designation, it is required that these letters and numbers are written in particular sequence. Each letter or number will indicate a particular method of manufacturing, particular type of coating, particular position of welding, particular welding current, particular set of mechanical properties, or the special characteristics of the welding electrode. Okay, now I'll show you one PPT which will give you enough idea of what I have just said. Yes, so here this is the Indian standard method of electrode designation. What you can see here is this. We can use the letter E or R. E stands for extrusion method, or extrusion followed by the reinforcement of certain constituents. So we can use either E or R. When it is E, it shows that electrode has been produced using the solid extrusion method. The second character is the number, which shows the type of the coating. Okay, so here it is 3, means the appreciable titanium fluid slag type of the coating. So these are the various types of the coatings which are commonly used: high cellulosic, high titanium, viscous slag, appreciable titanium, the fluid slag. Fluid means thin slag basically, which has having the low viscosity, high oxides and silicates of iron and manganese, high iron oxide. So likewise, that certain numbers are given to particular type of the coating. Okay, so that's what is visible here. The second number indicates the welding position. Like say 0 is for the electrode suitable for all the welding positions. When electrode is given 0, second digit is 0, then it means it shoots for all positions. When it is 1, it shoots for certain set of the positions. It is 2 means it is suitable for flat and horizontal positions. 3 is only for the flat positions. Okay, next digit is 5. That indicates the type of welding current. So whether it can be, it shows the type of polarity to be used and the current magnitude. Okay, like 0 to 9. Okay, the type of polarity, whether it is DC positive or DC negative. Okay, DC state polarity or reverse polarity. So D positive means reverse polarity, D negative means state polarity, and the current magnitude. Then set of the 3 numbers. This indicates set of mechanical properties, like 3110 to 411 means its mechanical properties are in the range of 4 strength is tensile strength is the range of 410 to 510, minimum yield strength is 330 in all these cases. Okay, in 500 series it is 360. Minimum elongation is 20% elongation, and minimum temperature at which the toughness is 47 joule is this 27 degrees centigrade. Okay, so this is about the third digit indicates the set of 3 numbers indicating the mechanical properties in terms of tensile strength, yield strength, elongation, and the temperature corresponding to the minimum 47 joule of the toughness. The last character is a letter which indicates the special feature about the electrode. Say H for the low hydrogen or hydrogen controlled electrode, J is for where iron powder has been added leading to the 110 to 130% deposition efficiency, K is for 130 to 50%, 150% efficiency, and greater the L is for the deposition efficiency is greater than 150%, and P is for the deeper penetration. So this is how the electrodes are designated, and this is their significance. It is very important here, I must mention it again, that these parameters must be written in particular sequence only. Okay, so set of 3, so starting with E or R, then 3 numbers in sequence indicating a particular welding type of covering, welding position, and welding current, then set of mechanical properties, and then special characters which can be like P or J or K or L or anything, H, anything. Okay, so that's all from my side. This was about the electrodes. Okay, so